And today I'll be talking about my project where I looked at repurposing drugs for HIV treatment using machine learning to scale up local production in Africa. So I'm going to start off by asking you to think about this symbol of the red ribbon that the people are holding. What does it make you think of? And have you seen it before? So I actually came across this symbol for the first time last year. When I was looking at using gene editing to both cure and prevent HIV. And I was surprised to see I didn't know anything about HIV until last year. When a lot of people had talked to me about HIV up until I started doing research into gene editing, they had talked about it in the context of the past, so in the 80s, but not really about HIV right now. And I've noticed that that's the case for a lot of people, where they think that HIV is something that's done. The pandemic is almost done now, but we're actually still in an HIV pandemic. And there are people in the world who still don't have access to HIV treatment. In 2020, there were 37.6 million people in the world who were living with HIV. And each year, 2 million people are added onto that number. And 68% of the people living with HIV are living in the hardest hit region of the world in the African continent. And every year, 2/3 of the people who are newly infected are from Africa. But the thing is that only 64% of the people who are infected with HIV in Africa have access to HIV treatment called antiretroviral therapy, or ART. But for your information, ART is not a cure for HIV. It's just a treatment. What it does is that it reduces the viral load in your body so that HIV cannot be transmitted, or for HIV to progress into AIDS, which is the deadly part of the disease. Just until a few years ago, the biggest barrier towards giving access to HIV treatment in Africa was the price of ART drugs. But since 2018, this new type of dulaglutide combination ART drugs have been produced in India and imported to Africa for just $75 per patient for a year's supply. And this is a great price compared to North American countries. This is almost like just a fraction of what North American patients have to pay. But still, there are 36% of people who are missing access to ART drugs. Particularly during the COVID pandemic, the availability of ART drugs was reduced so much in South Africa to the point that some people were left without any ART drugs. And the bottleneck that I identified was importation. So African countries import most of their ART supplies. In 2015, they imported 98% of their supplies. Only 2% of them were being produced in countries like South Africa, Zimbabwe, Uganda. But importation is causing a big bottleneck, especially during a pandemic like COVID. And it could potentially cause a crisis where people don't have any access to HIV drugs because of a lack of availability. So this made me think about why aren't African countries not producing it themselves? If importation is causing such a big problem, then why not just produce it locally? And I found out that active pharmaceutical ingredients of ART drugs are too expensive in African countries. They're around $120 to $800 per kilogram for ART drugs. And that's just too expensive for them to produce locally. Whereas in comparison to a diabetes drug like glyburide, it is much less. It's $43.1 to $115.2 per kilogram. So knowing that the price of the active pharmaceutical ingredients is so high for ART drugs, by the way, an abbreviation for active pharmaceutical ingredients is APIs, and I'll be using that a lot in today's presentation. So knowing that they're so high, and that's the reason why it's stopping local production of ART drugs in Africa, so that there could no longer be a problem with accessibility and availability. I asked myself if I could use machine learning to repurpose drugs with a lower API cost for HIV. And the reason why I decided to use machine learning was because it's much smarter than a human. Imagine if you're looking for a jewelry in sand Are you just going to do it like with naked eye, or are you going to use some sort of metal detector? Machine learning here is that metal detector. It's a tool for us to optimize our tasks. And machine learning, more specifically, is a subtype of artificial intelligence where you teach a machine to carry out a function for you. And you can teach your machine in 3 ways: through supervised learning, unsupervised learning, or reinforcement learning. In supervised learning, you're providing your machine with labeled data and their labels. So, for example, you have triangles, circles, and rectangles, and you're also providing the labels of those to your machine. You're saying that it's a rectangle, it's a circle, and it's a triangle. Your machine will learn to associate the shapes with the labels. And when you provide it with new test data, it's able to predict the label of the new test data. However, with unsupervised learning, you're just providing the data and no labels. So you're giving the machine a picture of a star, a circle, or a square, whatever your data is, and the machine will learn to be able to categorize those shapes. And then when you provide it with new test data, it's able to predict it and say, this is a star, this is a circle, but it won't be able to give it a label. It'll just say if the circle is similar to other circles, or if the star is similar to other stars that it's trained on. And reinforcement learning, the third type of learning, is a type where it uses reward and punishment for the machine, similar to how you would teach a baby when it's very young. So what it does is the machine carries out a prediction, and if that prediction is right, it's going to reward itself, and it's going to send that state of correctness back again to itself, and then build on top of that for the next prediction it makes. And the punishment isn't really a punishment, but it's basically to discourage the machine from making the same prediction again if that prediction is wrong. I work with supervised learning because supervised learning is usually applied in bioinformatics and chem informatics, which is the area I was working in. And there are 2 types of supervised learning. There's regression and there's classification. So with classification, you're basically just putting your data, your test data, into classes. So for example, the class of circle or star. But regression can give you a specific numerical value. In the case of the shapes, you can't have a specific numerical value. But let's say you want to predict the temperature outside for the next week. You can't use classes there. But what you can do is predict the actual temperature. And regression does that for you. So machine learning can be applied anywhere throughout the drug discovery phases. The first part, which is drug discovery, we can start off with target identification. This is where you identify a disease target and you can validate it. Machine learning can be applied here to identify that disease target. The next step is hit identification, where you're identifying from a large number of small molecules which one of them are active against the disease target you previously identified. And during hit identification, the process you're using is called high throughput screening. I'll be talking about that in a bit. And then next step is hit to lead, where from those hits that you identified, you narrow it down even further into small molecules that are even more specific for your disease target. And then you're going to optimize that lead so it's the best molecule possible before it goes into the development phase, where it's tested out in cell lines, in animal models, and potentially even into clinical trials. So I said I'll talk about high throughput screening. So high throughput screening is a process where you have a bunch of small molecules and you're screening them to see which one of those are active against your disease target. And by the end, you're going to have a small number of small molecules that you could take to the next step in a drug discovery process. So before this, I was talking about regression. Let's go back to regression a bit. This equation, as you see right now, I think a lot of people have seen it in high school. It's one of the most fundamental equations of math. This is the equation for a linear function. It's where you can predict the value of y from the value of x and other variables. So in machine learning, x is the data that we're inputting into the machine, and Y is the value we wanted to predict. The A and B here is what the machine will be trying out. So when it's training, it's going to come up with this equation so that it can predict the Y value when we introduce new X values to it. In my case, my X values were the molecular structure of small molecules, and my Y value was the PIC50 value of these small molecules. PIC50 is the negative log form of IC50 value, which is a measurement for the potency of a drug against the target. And with that, I collected my data from the CHEMBL database. The CHEMBL database has data on the molecular structure of a bunch of small molecules that have been tested out against many types of disease targets, and it also has their IC50 values. And then I also used the regressor, which was originally developed by Chan and Nandasanama, and from there I was able to predict the potency of small molecules with lower API costs on HIV targets. The HIV targets that I chose to work with were the HIV reverse transcriptase and the CCR5 target. So starting off with the HIV reverse transcriptase, this is a molecule that's very important in the HIV virus because it helps the virus replicate its DNA and then later on integrate itself into the genome of human T cells, which are the cells in our body that are infected by HIV. So this molecule is imperative in infecting humans. And a lot of current ART drugs work to inhibit the reverse transcriptase. The next target I worked on was the CC chemokine receptor type 5, the CCR5 target. The CCR5 target is actually on human white blood cells. It's not on the HIV virus itself. It's been shown that in people with mutations in the CCR5 receptor, that they are immune towards HIV. So if you're able to inhibit this receptor, it'll stop HIV from entering cells and thus infecting them. There are currently a small number of ART drugs that are being developed for CCR5 inhibition. So my goal here was by choosing two different targets to be able to come up with small molecules for a target that's been used for a long time now, and a target that's recently being developed. And my workflow went like this. So I first started by pre-processing my training data. My training data consisted of molecular structures of a bunch of small molecules that had been tested against my HRV targets and their IC50 values. My test data consisted of the molecular structure of small molecules with lower API costs, but not their IC50 values. That's what my model would predict. Then I tested out a bunch of regressors to see which one would be the best to use. And my measurements for best was lowest time of prediction and also highest RMSE score. And then from there, I figured out that the light GBM regressor was the best based on the measurements I used. And then I trained the light GBM regressor on my training data, and I tested my test data on it. So because the number of features in my data was so big, as you know, with molecular structure of small molecules, there is a lot of atoms there, so there's a lot of features to account for. So I wasn't able to predict, to calculate the accuracy of my model. Instead, I visually represented it on this graph by comparing the experimental PIC50 value of those small molecules that I trained my model on and the predicted IC50 value of them. And on my test data, the results that I got were that glyburide is the only cheap API drug active for reverse transcriptase. And to my surprise, glyburide was again the only cheap API drug active for CCR5. Glyburide is a small molecule drug that's used to treat diabetes mellitus type 2. What it does is it stimulates your pancreatic beta cells to release insulin. So I was so surprised to see that glyburide is active against not one, but 2 HIV targets. It was quite unexpected. And to really confirm this result that I got, I would need more data. So what I worked on was just a prototype. I had only a small number of small molecules with low API costs because I made the data set myself. But with more data, this result with glyburide could be validated further. Also, I would need to try out more models. I only worked with the IBM regressor. I'd have to try out other types of regressors or even neural networks. And if both testing out more data and more models proves to increase the accuracy and like the validity of my results, then we would have to do more testing with cell lines and animal models for it to actually be put into context. But the advantages of being able to reduce the cost of ART drug production in Africa to be able to scale up production in that continent is great. First of all, you're creating jobs by scaling up production in African countries, and thus it reduces unemployment in those countries. Second, when Brazil scaled up their production of ART drugs, they were able to save up to $200 million in 3 years. And African countries can also take advantage of this saving. Also, because the majority of the people in Africa who have HIV are part of the working population, so between the ages of 15 to 24, if they are healthier, if they have access to HIV drugs and they're healthier, then they're more productive. And finally, with more people accessing HIV treatment, it'll help us reach the UNAIDS 1990 goal faster. So the UNAIDS 1990 goal, one part of it is to have 90% of people in the world with HIV have access to HIV treatment. And also, lastly, the other benefit of this type of workflow is we could apply it to other types of drugs in low-income settings. For example, with malaria, to be able to find lower API drugs for malaria, so we can scale up production of malaria drugs in African countries. And to sum it up, the goal here, basically it's to increase availability and accessibility of ART drugs in African countries, and thus, at the same time, making their economies more sustainable because they're able to locally produce drugs that they're very reliant on. Going back to this image, for me, at least personally, it was a surprise to find out that the problem of HIV is still pretty prevalent, and there are a lot of people still in the world, maybe not where I live, but in other corners of the world who are still affected by this problem and who still don't have access to treatment of it. Like they can't even have this disease under control yet. And hopefully, by being able to leverage emerging technologies like machine learning and gene editing, because that's what I focused on a lot last year, we're able to bring access to HIV treatment to anyone who's suffering from this disease. And personally, the impact of this project on myself is it has excited me to see the potential of drug repurposing for other type of disease targets and to see where this type of workflow can lead us with drug discovery. Thank you for listening to me. You can connect with me on LinkedIn, YouTube, and Medium at Diba Dindus. Thank you.